Science tells us that thunder is caused by a tremendous vacuum. A lightning bolt heats the air in its path, causing it to expand and leave behind just a space where the air used to be. Waves of air rushing in to fill the empty space produce the actual sound of thunder. This tendency of air to rush into empty spaces is also one of the principal causes of storms. The air around us exerts a pressure on every square inch of surface exposed to it. In the weather forecasting stations, sensitive instruments show that this atmospheric pressure varies occasionally because of local weather conditions. When the pressure in one locality becomes temporarily lower, the weatherman knows that winds will blow as great masses of air rush in to fill up the space. Special maps are made to chart these variations in pressure, to help trace the paths of winds which may carry rain or snow. These low-pressure areas are created naturally. We all see illustrations of the action of artificially produced low pressures in our daily lives. When we drink through a straw, for instance, suction on the straw creates a partial vacuum so that the air pressure in the straw and in our mouths is less than the normal air pressure on the surface of the liquid in the bottle. This difference in pressure forces the liquid up to fill the empty space inside of the straw. By drawing in air, the smoker reduces the pressure inside his cigar. The normal air pressure on the outside forces the smoke through the cigar and into his mouth. When the rubber disc of a suction cup is flattened, the air is forced out. When the cup springs back to shape, it forms a hollow space with very little air in it. The normal pressure on the outside of the cup holds it against the wall with considerable force. In an airplane, the rapid movement of the wing through the air causes differences in pressure. The shape of the wing and the angle at which it is set causes the air rushing past it to crowd against the lower surface, increasing the pressure under the wing. For the same reason, the air rushing past the upper surface leaves a gap and lowers the pressure on top of the wing. The difference between the high pressure under and the low pressure above forces the plane upward. Scientists say that most of the lift is due to the extremely low pressure or partial vacuum on the upper surface. Although even the most advanced science has not been able to produce a perfect vacuum or space in which there is nothing at all, the next to nothingness we call a partial vacuum can be produced and controlled. We can create a partial vacuum if we first fill a glass tube with mercury to drive out the air. When the tube is upended, the mercury falls, leaving an almost empty space at the top. The mercury remaining in the tube is held in place by the weight of air pressing on the surface of the mercury in the dish. If normal air pressure in one side of a U-shaped tube is increased by pushing a piston down, the pressure will force the mercury up in the other arm. When we pull the piston up, we reduce the pressure. Normal air pressure on the other end will force the mercury back again in the opposite direction. A suction pump can be used to remove most of the air over a piston in a glass cylinder. Normal air pressure trying to fill the partial vacuum exerts force enough to support a considerable weight. A great deal of progress has been made in the control of vacuum and in the use of vacuum to control other forms of power. In a player piano, a pair of bellows creates a partial vacuum. Holes in the music roll allow air from the outside to flow through different openings to fill this vacuum. These streams of air move the hammers, which strike the different strings. In this heavy-duty vacuum cleaner, large fans lower the air pressure in a hose connected to the furnace. Normal air pressure rushing down the chimney carries with it the soot and dirt and forces them through the hose into a huge bag. This same vacuum force is put to work in modern city post offices. Mail is placed in containers made to fit snugly into large pneumatic tubes. A partial vacuum ahead of the container permits normal air pressure behind the containers to force it through miles of tubing at lightning speed. So the power of empty space has greatly increased the efficiency of Uncle Sam's postal department, and has made possible the delivery of letters and parcels in less time than ever before. The latest successful application of partial vacuum to reduce work is in the automobile. Automotive engineers knew that the comfort and safety of the modern motor car could be increased by making it easier and more convenient to shift gears. The fundamental operation of the gear shift lever is simple. When the knob on the shift lever is moved in one direction, the bottom of the lever moves in the opposite direction. The movement of the bottom of the lever causes the right gears inside the transmission case to mesh with other gears to drive the car with the right speed. Now, suppose the gear shift lever is taken off the floor and moved to the most accessible, convenient position, right alongside the steering wheel. The method of shifting is the same. Although the lever has been turned on its side, there has been no change in the shifting movements. The next thing is to connect the shift lever to the gears themselves. A long rod connected to the bottom of the shift lever will transmit movement to a crank at the other end of the steering wheel post. And another rod and crank will carry the movement back to the gears. Now, when the shift lever is moved, the system of rods goes into action and selects the required gear. But this is only half the job. After the gear has been selected by the up and down movement of the shift lever, it has to be shifted into position so that it will mesh. Another rod is needed to do this half of the job of shifting gears. And to make the system more compact, the second rod can be made hollow so that it will slip right over the rod already in place. To separate its motion from the back and forth movement of the inner rods, this outer rod or tube can carry a twisting movement instead of a push-pull. The twisting motion of the outer rod will turn another crank at the bottom of the steering post. And this motion can be passed on to the lever, which does the actual shifting. With this arrangement, any movement of the gear shift lever carries a corresponding movement to the transmission. This is simple. The selection of gears is almost effortless, but the actual shifting takes a certain amount of work. A lever 2 feet long and moving 10 inches changes gears with ease, but a long lever on the steering post is inconvenient. A shorter gear shifting lever is more convenient, but since the movement is shorter, more effort is required, especially in cold weather. The latest development is to let the normal air pressure of the air around us do the actual work of shifting the gears. In an automobile engine, moving pistons act like pumps, creating a partial vacuum to draw fuel into the cylinders. A vacuum chamber connected to the intake makes use of this reduced pressure. A movable plunger divides the chamber into 2 separate sections. Now, when air is drawn out of one section of the chamber, lowering the pressure, the normal pressure in the other section will drive the plunger, exerting force on every square inch of its surface. By reversing the operation, the plunger is forced back in the opposite direction. A sliding valve controls the action with the slightest movement of the shift lever. The plunger is connected so that it transmits force directly to the lever that engages and disengages the gears. With so little effort required to shift the gears, and with a minimum of movement, the gear shift control lever can be brought down to a still more convenient size. The power of vacuum permits a shorter lever moving a shorter distance. The hand merely applies the power, and vacuum does 80% of the work of gear shifting. Again, engineering design has moved forward. Driving has been made easier for everyone. The power of vacuum shifting the gears makes fingertip control possible. With a minimum of effort, the driver is able to keep control of the car at all times and to shift gears at will according to actual driving needs. A flip of the finger, and in second gear, steep grades are taken with the car in perfect control. No muscular effort is required. there's just enough resistance to let the driver sense the feel and timing of the gears. With this modern easy shifting, another improvement for safety has been made in the newest automobiles. The emergency brake has been moved up out of the way and conveniently located on the dashboard. There is greater convenience for today's motorists than ever before. Taking the control levers from the floor has made more room and more comfort for the driver and front seat passengers. And because we can now enter and leave the car on the side away from the traffic, greater safety for all.